Yeah, so let's have a quick recap of what we did last time, just so you can ask questions. We had label cover, you know, our favorite. We have small things to the left. We have large labels to the right. We have projections. We wanted to do 3-sat with perfect completeness, so then we picked some probability distribution. We picked x and y at random, and then we set z according to this. So if x was false, we would make sure that one of these were true, and otherwise we would sort of make zi. Well, I got this wrong, right? And then it turns out, compared to previously when we didn't have this for certain, we got much worse correlations between y and z. So that sort of made, there were two ways to get around this. Either you sort of picked a random bias parameter, which sort of has been used once more. Well, I use this to make a commercial for myself. Okay. So the only sort of, after what I've done in this lecture, the only thing of arity3 which predicates are approximation resistant is a max not 2 predicate. This is the one that's true if and only if there are not 2 true literals. So this was known from a long time ago that it was hard to approximate within 5/8 plus epsilon. 5/8 is the random ratio. And in fact, this is true also for satisfiable instances. And that needed some more technique. And then, in fact, I need to combine these two ideas to make that proof fly. So this was in approx like in a year and a half ago. So the more important technique that's been used lots of times is to have a smooth label cover. And the smooth label cover is the property that if you take any two labels in any set here, the probability of a random neighbor that they project on to something is small. And you can make this as arbitrarily as small as you want. And that's sort of an important, if you're ever going to work with label covers, have smooth label covers in mind, because they might turn out to make life easier, and they exist. Okay?
Why doesn't this work for max not 2?
Pardon?
Why doesn't this work for the satisfiable case of max not 2?
The thing we just did?
The smooth L3?
Just the smooth, right? So what you have to do is you have to avoid, so here we are avoiding, in fact, if you look at the assignments on 3 bits, we're avoiding 2 of the 8, okay? So you need to avoid 1 more, okay? And this in particular means that y can't anymore be independent of x. So so either y or z has to be dependent on x if you're going to just have the distribution on the max 2 predicate. And that sort of creates additional complications that you have, yeah. You have more things to worry about. Since you now have a correlation also between x and y, it's worse. That paper also has a world record in so one thing you kind of noticed is that I got fairly good dependence on the epsilon and deltas in the max 2 lin, and it got much worse in this max 2 set, or in the max 3 set. And in the max not 2, it gets horrendously worse. So I moved from a polynomial in max 2 lin to sort of exponential dependence in max 3 sat, and in max not 2, there's sort of a tower of exponentials that's on the height of 1 over epsilon in the constants. So it gets worse. Yeah, but the important thing is smooth label cover. And once we did that for 3 sat, it wasn't too hard. It was moderately, if you sort of accepted with 7/8 plus epsilon here, you had some calculations, and then you could prove that the sum of this type, where alpha was a subset of beta and beta were moderately small, was large. And then we got, this immediately gave us the same probabilistic labeling as before. We pick random alphas and betas with this probability in random elements. And the fact that this is sum even sum is large even over small betas was enough to save us. Here. And then I suggested homework, that you should do this for 4 sat. You should do it with 4 lin and with right hand side -1. Who did the homework? Great. You want an apple or do you want?
I only did half of it, so maybe I only deserve half an apple.
Well.
Oh my god.
So what was the result?
So I did Forlin.
Yes?
And yes, so you have to probe twice on the left side and twice on the right side.
Okay.
So I took x and x prime on the left side, independently, I guess.
Yes?
Then I took y on the right side.
Okay. This is random? Uniform?
Yeah.
Uniform? Uniform, yeah.
Yeah, and then I took y prime to be the product of minus x times x prime times y.
X by I.
Yes, x pi, yeah, projected, lifted.
Yeah.
And noise, mu I.
Yeah, with UI. Yes.
And then you do it, and it's not, you don't fold. So the even terms are still there, but they turn out to be your friends.
Yeah.
And then it's even easier because the sum that you get is just begin with this f hat squared times g hat squared. So
Yeah. Yeah, you immediately get the sum f hat squared, g hat squared. But then you have a minus 1 to the beta and then a 1 minus 2 delta to the beta or something, right?
You must show this is at most something.
Yeah.
So it's even, I think it's beta minus, the exponent is beta.
Yeah, it depends on what you put in front. Yeah.
So
Maybe
you
plus
can
1.
just ignore the
So the point is that the dangerous term when these are the empty set have the right sign and then we're home. And it's actually a lot simpler. So you just have to make sure that the empty set goes your way and then you're done. Nobody tried force-hat?
Well, tried but failed.
Okay. So you want to report something or?
So one thing you can try, so I think 1 query and 3 on the right should work.
Yeah.
But you cannot, so here's something I tried and doesn't work is that you pick one and independent of it. So if you picked it as 1, between 1 minus 1, if you picked it as false, then you can try to take the parity. And if you picked it as true, then you take the noisy product distribution under 3.
Okay.
But this doesn't work because you get the same kind of terms.
Yeah. So you have to pick a.
Right. So this is 3 independent. That we can't pick the distribution to be 3 independent.
Yeah.
So that's the,
Yes, you want some noise also in the question on minus when the first one is true, right? So you don't want to pick when it's true. You don't want to pick pure parity. But I must admit, I know this is easy, but I didn't do my homework either, so I can't do it. So I hope that some of the students could do the homework. But we can. I can. If you're interested, I can do the homework and do it tomorrow. But you should get, chocolate. You want apple?
apple is good. Well, I got 4 links, so.
What?
I got 4 links too, so the big apple.
Good. So what we wanted to do next is move to. So the point of this exercise was to prove that it's actually easier when things get wider. You have more degrees of freedom and things are better. So what happens when you go the other way and you go to smaller predicates is that you have less degrees of freedom. And I sort of briefly asked, could you have a direct PCP there? And the point is, if you have 2 questions, you can't. I said before, if you want to do this by the Fourier analysis, you really want questions that's uniformly random, each on their own. And then there's very little you can do if you have a uniformly random question here and a uniformly random question there, because they don't have anything to do with each other. You really need these 3 questions to go somewhere. But there's one way you can get around it. Okay. And let's assume that pi here is a 1-to-1 mapping instead. Then in fact you can compare a random question here with a random question there. So if we sort of could get pi to be a 1-1 question, right? I mean, the problem here that all the things here that project onto the same thing there sort of gives all the correlations and stuff. So does anybody see any problems of having this 1-1? I mean, we didn't get it 1-1. The question, could we get it 1-1?
Well, you can't get perfect.
Yeah, so you can't get perfect completeness because then if you have a label here, you know what the label is there and you can sort of go back and forth. So I don't know if I'm going to get to this. So this is a unique game conjecture that says that for any epsilon, you can have completeness 1 minus epsilon, soundness epsilon, pi to be 1 to 1, and yeah, L equal to S, of course, since you have a 1-to-1 mapping, but L, of course, will have to depend on epsilons. So if you decide on a certain tolerance for the error, there is a certain label size, so you can have these labels 1-to-1, and this is still hard. And this is the unique games conjecture. For those who didn't see it. And once you have the unique games conjecture, you can do lots of things. In particular, it gets a lot easier to work with these predicates of arity 2. But for now, I don't want to work with those, but I'll sort of want to do NP completeness. Okay? Yeah.
Even in the case of UG, as Dominic was mentioned to me a little while ago, even if you assume UG, your Fourier expansion, when you write the problem, you just get product of two terms, and Cauchy-Schwarz is not good enough there. So how do you handle?
Well, now you're into yeah, wasn't really. Of course, yeah. It's if you're going to do sort of one question there and one question there, you get into these majority stablest kind of things, right? I mean, you can sort of do interesting things. You can at least have a random question there and say something about the random question there. Yeah. I don't know if I should devote last lecture to this. That's to unique games. I've changed my opinion of unique games. First, it's so much fun to assume unique games because you can prove so many new things, and then suddenly people start doubting unique games, and then you say, well, let's prove NP completeness again. And this lecture series was supposed to be NP completeness, but we can see if we get to unique games. But at least that sort of makes life a lot simpler in this situation to have 1-to-1, because you can get rid of these dependencies between the various bits that project onto the same thing. So the thing I want to discuss is what I started discussing last time, is sort of gadgets. And the thing I ended with last time was sort of a gadget reducing 3-sat to 2-sat, which had the property that I started with one 3-sat clause, and then I made 10 2-sat clauses in these 3 original variables and 1 auxiliary variable, with the property that if this was satisfied, there was some value of A that satisfied exactly 7, while if this was not satisfied, both for all A, A true and false, it's satisfied at most 6. And then you just apply this to each clause in a 3-set formula with different values of A. Of course, X, Y, and Z will be the original guys, but one new A for each clause, and then you could get a 55 over 56 inapproximability for max 2-sat, where this number, that's a function of 7, which is this number, and 7, 8, which is the inapproximability for 3-sat. Okay. So what I want to discuss today is, well, how good the results can you get from gadgets? Can you find the best gadget? Is this the gadget I presented? Is this the best gadget to go from 3-sat to 2-sat? These kind of questions. Okay. So this is not my results, by the way. So most of what I'm going to say today is Trevisan, Sorkin, Sudan, and Williamson. Okay. So let's try to be formal. We take one constraint of P, we make K constraints of Q, of type Q, and I want to say, so P, so
Johan, this
Go.
becomes almost invisible.
okay, thanks. And I might even assume weighted guys here. So the idea is that, the auxiliary variables will sort of take care of the fact that these are sort of different constraints. If this condition is false, they will assume that the maximum over the auxiliary variables is some W. And when this is false, the best is W minus 1. And once you have something like this, an inapproximability for P together with the value of W will give us some inapproximability results for Q, right? And now you can say, well, this is just up to ingenuity, right? That how do you find the best gadget? And this is how people did it for 30 years, because this was sort of, or 20 years at least. But let's think about this a little bit. Okay. And let's, for a while to be concrete, let us think of this as 3 lin, and this is 2 sat. Okay. Suppose we had something that looked like this. Right, so let's mentally, so we've sort of made some we've started with an equation, x1 times x2 times x3 equal to 1. We made this into a number of equations, x1 times a1 is equal to 1, x1 times a3 is equal to minus 1, and so forth. Somehow. And the way I want to think about these is that, well, let's at each good assignment per piece accepted, let's write down the values of A that witness this, that we can satisfy total weight W. And suppose this table looks like this. We had 5 variables. So my question is now, did we need 5 variables? 5 auxiliary variables.
Well, they're linearly dependent over.
Yeah, they're linearly dependent. I mean, if you have enough, they're going to clearly be, is this bad or? Yes?
So, like A3 is always one of these good cases. That seems like weird. I mean, if you build a gadget and then you fix A3 to 1,
Yeah.
it sounds like it should still be a good gadget.
Yeah, so this is sort of saying that so A3 is 1 always.
A1, A4, A5, and
So the point is I could just cross it out there. So if you sort of look at the two conditions, this is 1 and this is 2. It doesn't hurt condition 1, right? And because we still have the same optimum if we fix it, because that's what we wanted of A3 anyhow. And the point is can only help in 2 because we give less freedom in these cases. There are less possibilities for the auxiliary variables, so we can only get better soundness sort of in the reduction. Okay? So who said, well, you already got an apple. But I heard other good comments sort of.
Yeah, linear independence.
What?
Linear independence in the logs if you want.
Why linear, what's linear independence? Why is this?
Because you can replace it, let's say here you have A1 equals minus A2, so you plug it in, but you could also have A4 is A1 times A2. You throw that out.
Suppose A5 is equal to A1 times A2. That's what you're saying, it's linear independence. So?
Throw it away.
What do you throw away?
A5, and write instead A1, A2.
But that will create an equation with 3 variables. I'm trying to make the two-lim. Yes?
I mean, these linear dependencies between A1 and A2, this you can do, right?
Yeah.
And what Matti said, there you can, of course, replace.
Yeah, so if A1 is equal to plus minus A2.
Unless you insist of right-hand side being minus 1 or something like that.
No, I'm not, right?
You're not. Oh.
I'm doing two-lin, which is...
Oh, you're doing two-lin, you're not doing two-sat.
Well,
Two-lin.
good. If I'm doing... So would it matter if I was doing two-sat?
No?
No, because I have negation for free also there, right?
Yeah.
So suppose A2 is equal to minus A1. So I claim that whenever A2 appears, I'll replace it by minus A1, or in the two-sat notation, A1 complement. Which again will have the property that since they are each other's negation, in the positive case, for 1 I'm doing equally well, and I'm only restricting the power of the sort of bad guy in 2. I mean, it's easier to prove soundness because I have less cases. Okay. So as you noticed, A5 and A4 are also each other's negation, so I can get rid of A5. I already get rid of A3. I got rid of A2. So A4 is A5. I did minus A4, and A1 I did my A1. Yeah.
So in fact, A1 is X3.
What?
A1 is the same as X3.
Yeah, A1 is X3. Is that bad, or can we replace also by primary? Can we replace auxiliary variables by primary variables?
No issue.
Yeah. What was it?
X3.
So then we only have I4. Okay. So this means in this case, how many auxiliary variables do we have? or for primary variables. No need for constants. Right? Or equal. Right? Two auxiliary variables that always took the same value, we don't care either. How many do we have? How many auxiliary variables could we possibly need them?
Two to the number of satisfying assignments, and you get rid of the all ones, all minus ones, and the original assignments, and pair them up.
So first of all, we have negation for free, right?
Yeah.
So that sort of gives
division by 2.
That's
Okay.
And then we sort of get rid of the constant.
The constants.
And then we get rid of the 3 primary variables.
So it's 4.
It's 4. So we only need 4 auxiliary variables. Okay. So that's a good start, right? That sort of means that we have a finite object at our hands, which was not completely obvious to start with. Maybe we should get rid of this.
So is this idea before the paper?
I don't think so.
It is a very nice and simple observation.
Yeah. Yeah, that's why I like it. It's nice and simple, right? No, I think that was new. I don't... Yeah, it's sort of, once you sit down and think about it, instead of sort of playing around with all these things, it's really tells you how you should do these things. So we have 3 primary variables. We have 4 auxiliary ones. So this means we have 7 choose 2, which is what? 21 left-hand sides. We have 2 right-hand sides for each, they can be plus minus 1. And we have 7 equations. We're allowing now. It's sort of not obvious whether I allow an equation like x equal to 1, but I'm going to think of this as a Tooling condition also. Okay, it's not needed. If I somehow you have to check that when you're replacing things here, you're replacing something by its negation, but I also want to get rid of constants. So that means if I had something with depend on 2 variables, I now get something that depends on 1 variable, so I have to allow 1 variable things to appear also. Okay. And 2 right-hand sides for these. So this is 42 plus 14. So this means I have 56 possible equations. So I said I would allow weights. So now let's just try to look at what kind of weights do I need. So I'll just introduce a variable for the weight of equation I, Wi. Okay.
Weights are necessary because otherwise we could not collapse
Yeah.
multiple copies of the same equation.
Yeah, and it sort of we could allow repetitions and so forth,
then
right?
It's not clear. It's no longer a finite object if there are repetitions.
Yeah, no, yeah. So originally I didn't really tell you, but I said I had a weighted version to start with, right? We would get, and now we add we collapse things and add up the weights, and we have. So I claim that 1 and 2 are just linear inequalities. Double rise, right? And
excuse me?
yeah,
I kind of see it for 2 because you just for every, if you give me the x's, I just write down for everything I can say the a linear inequality, but this existential quantifier bothers me.
yes.
Say max.
Well, on top of it, good. So the existential,
Well, you can write 1 for each possibility.
no, so
I have an or of inequalities, right? That's weird.
it's an excellent point. Okay. So the point is, on top of it, I know for each assignment what these auxiliary variables should take. That's sort of what defines the identity of an auxiliary variable. Right? So I know that, you know, for the first satisfying assignment, A1 should take this value. That's how I define sort of the auxiliary
Okay,
variable.
what's this table you had?
Right? This is the table I had. So we said these particular values should in fact give the weight W. And all other values should give at most W, because I want to sort of to be on target. But the particular values that define the auxiliary variables should give W. So that's actually linear equality for this value, and inequality that you don't beat W anywhere else. So that's a good point. Thanks. You want a chocolate?
Yes.
Everybody happy? So now we just write, we're computer scientists after all. We have a linear program and we just solve it. I mean, we just have 56 variables, and we have 8 different values for each of these assignments to do, and we write down an LP, and then we run it, and then we get something. Well, let me draw it rather than... So there's a nice way to draw this gadget that you get. So you take the 3-dimensional cube, on edges, inequality. And in fact, I'm sort of cheating here, so I claim now I have 1, 2, 3, 4, 5 auxiliary variables, but the thing there is identically 1, so it's the constant 1. So I have some equations of weight 1, and then I have... This is the gadget that comes out. That's the optimal gadget for 3 sets to tooling.
So you're solving feasibility or minimizing W?
Yeah, you need to minimizing W, right?
Sorry, I didn't get to the last discussion.
Pardon?
So you're saying this is the best?
This is the best gadget to reduce 3-lin to... Well, what did I say I was going to reduce to?
What? You said 2 sat.
Yeah, but I meant 2-lin. Okay. Everything applies. So the 2-sat, I can write down the 2-sat gadget in a moment, but this is the 3-lin to 2-lin gadget. Sorry.
So So equalities on edges, inequalities on
diagonals, main diagonals. So going all across.
all the way.
Yeah. So this sort of shows that it's hard to approach Toolin within 11 over 12 plus epsilon for all epsilon. Okay.
And where is the what's the gap?
Should we check this?
We just need to calculate total number of equations.
So we have
12 equations.
16 equations, and in the good case you can satisfy 12, and in the bad case you can only satisfy 10. Well, we happy to do this?
Oh yes, 10.
So if x1 times x2 times x3 is equal to 1, we can satisfy 12 equations. Okay. So this is checking, okay? So now you have to make sure. So this means if we can do 1 minus epsilon m in the beginning, we get 12m, 10m. And if we can just do half plus epsilon, we get and sort of, sorry, it should be 12, right? So in the good case we get 12, in the bad case we have only 10, so the reason for 11 is sort of the average between 10 and 12, and we started with a half, right? Good, so we can also do 2-set. I'm not sure if I'm... So in fact you can do 11 versus, I don't know, do you want to see this gadget? So 3 set, this is 3 lin to 2 set. Do you want to see the, guy wants to see it.
Yeah, is it a nice picture?
No.
Oh.
Second.
Do you want to see it?
It's sort of symmetric, but that's the optimal gadget. Okay. So good. So, yes, sorry.
Can I get a max cut gadget with the same method?
Yes.
Is it any good? I mean, I had kind of twice now of errors, right? Because like I can.
Yeah, so this skips first. Sorry, I was going to say this skips 21 or 22. Yes, you can get the max cut gadget also. Okay, so what's the problem in getting a max cut gadget?
I need more variables because I cannot.
We don't have negations. Okay, and on top of it, we actually have to start at, if we're going to reduce from parity, it actually, we don't have negation also on the starting side, so we need to look separately at equations x plus xyz equal to 1 and xyz equal to -1, and we have to make gadgets for both of them. So it gets a little bit more complicated, but you can get max cut gadget also.
Does it give you the best inapproximability ratio without any games?
It gives you 16/17, okay? Yeah, and that's the best I know. Okay. So now we want to do better. And now, and as far as I know, these three constants I just presented you are the best that's known with NP completeness. While if you assume unique games, you can do better. Yes?
So, were all these gadgets known before, or they were not put to be optimal in this paper? Or
Well, they were done in this TSSW paper.
so my question was, but these gadgets, did they exist?
No. They found them.
So they were earlier gadgets for reductions between these problems, and they improved.
Yeah, well, not all of them, but some of them exist. For instance, the 3-set to 2-set gadget I gave you last time existed before, but there's a better one that they found for that reduction. So now we want to do better, right? We want to beat these numbers. I want to tell you some ideas how one could possibly go about beating these numbers, and some I know don't work, some I don't know whether they work or not. And we'll sort of just discuss the idea. So maybe you can come up with some angle on some that's better, yes?
So, but this is all only for CSPs, right?
Yes.
Does this any of this machinery go through for something?
So what? But I'm just looking at very
So for example, vertex cover, can you claim the 7/6 is the best you can get by a gadget reduction?
But that's it's not
close
really
to a CSP, but not exactly. Right?
It's not really, yeah. So there we don't have auxiliary variables and gadgets really, right? We really have a big reduction from a proof with certain properties to a, yeah. So it's a different game. Okay. So let's see which any ideas. What come up? How are we going to do better? I just said we'll take 3 lin and we'll find optimal gadgets, and we'll.
Well, you can start from something else and find.
So what should we start from?
Label cover.
Label cover, yeah.
Yeah, that's but.
Or unique games. How about unique games?
Unique games is cheating. I already told you this, right? So we start with something we know is NP hard. Well, I've proved 2 problems hard, right? So the thing I proved so far is 3 lin and 3 sat, and I in fact worked harder to do 3 sat. To get perfect completeness, that's true, but maybe we should start with 3 sat. Could this possibly work?
Well, not for approximation ratios, right?
Why?
Because we already got a Sunlight approximation ratio from 3 lin.
No, the starting point.
Yeah, so this is a question, how do these compose, right? So the point is, you're right.
I mean, so 3 lin to 3 sat was a simple, if
Yeah.
we only wanted the approximation ratio, we got a...
Yeah, so the point is that...
So one thing is mysterious to me though.
Yes?
So you're starting from the long code. And the long code is the longest code you can create. So if you are creating, like let's say you are checking the long code with 3 lin.
Yeah.
And then you would put a gadget on top of that.
Mm-hmm.
So can't you just emulate it by just doing the long code immediately without like any in 2 steps? So
Yeah, sure. Yeah, that's one thing. Okay.
But can you do better with gadgets? I mean, is there like any situation when like if you put gadgets on top of this long code checking, you do better with the long code alone?
Well, we don't know how to do 2 sat with the long code alone, right? We construct. Or 2 lin.
So what?
Okay.
So what do these auxiliary variables do? I mean,
So it's between the two
sorry.
long codes. The auxiliary variables.
Sorry.
It's not only the auxiliary variables are not part of any long code.
Yeah, they are part of the on the edges of the long code.
Yes.
I
So
somehow.
they combine two long codes.
But doesn't it mean that there is a longer code, which something like that?
No, because each long code is only for one side, and now you combine both sides.
Yeah. So let's.
Yeah, but then.
Yeah. So there are two. It's an excellent chain. I have things to say. So So this is sort of a direct PCP type of thing, right? So you're sort of saying we have the long code. What could we possibly be doing? And the other is sort of have a different starting point. So the only thing I want to talk about this first, and then I want to talk about this. So, but the only thing I want to say so far about the second point is that 3-sat is no good, because we had this condition from 3-lin to 3-sat that I showed the first lecture, which in fact had no auxiliary variables. So in fact, whatever we do to 3-sat, we can just do a 2-step reduction, and we do equally well from 3-lin. So it will never pay to go to 3-sat. But let's take Mario's suggestion and in fact look at this in sort of, well, we had the long code, what possibly could we be adding? That's what you're saying, right? We had all the functions, we had so.
But this run is saying that somehow we are combining the two players, although
Yeah, but
of course there is this.
right, we have our favorite picture. We have, FU here, we have GW here. When we did 3-lin, we were sort of So this is something that I was thinking a long time ago, so let's think about it, okay? Right, so we had our label cover, we had the functions that we know well, and the parity test, and now we sort of, on top of this parity test, we add gadgets. So what do? Well, we now look at, let's depersonalize these a little bit. Right, so see if I can drive this message home. So whenever we sort of forget where these come from, these are now just variables in the unscrupulous provers trying to optimize things, and then we make a reduction, and in particular we'll introduce some auxiliary variables. But we know what these auxiliary variables should look like in the good case. Right, and we have a satisfying assignment. We know that the value of this auxiliary variable should in fact be, for instance, the AND of these two variables. Okay. So suppose we know that the origins of these two guys is in fact fu of x and GW y. So my point is, instead of making this sort of gadget variable, we know what it should look like. We know that if we form a different string of length, the big length, by doing the corresponding operation here, this very bit that already exists in our proof should in fact take exactly the value of the auxiliary variable. Right? And suppose the question sort of
questions can only help us.
Yeah, this can only help us because we're sort of using more information. Before we had the auxiliary variables, which actually produce different, I mean, could be used completely different in the different conditions. But now we sort of realize that we can reuse these guys. Okay. And I thought this was a great idea, but it doesn't work. Okay, so let's try to analyze a little bit why it doesn't work.
What do you mean it doesn't work? It still gives us, no.
Yeah, it gives the same. It gives exactly the same bound that we got through the gadget. Of course, it can't be worse, since we're reusing things that we before analyzed that they were independent. But it doesn't work. Okay. So what's the problem in trying to hope this? So now, when you're always thinking about such protocols, we should think ourselves as an unscrupulous prover. And now, well, this should be.
So what has this really done in terms of the distribution of the constraints over the two long codes? So now you have, instead of this one simple distribution, you have a combination of.
Well, this is just a string of my z prime belongs to L, right?
Right.
But as you're probably about to say, it doesn't have the uniform distribution. Okay. In fact, because this is random, but this, first of all, the bits are 3/4 0 or false. But on top of it, whenever this is false, everything that projects onto that bit is false. Okay. So it lives on -1, 1 to the L.
So the second thing is the real problem.
Well, both.
Well, the first you could just take minus the I.
Yeah.
No.
Yeah, but it has a very different distribution. So it's really that it's reading from a different table, because now instead of reading with the uniform distribution, we're reading with some distribution which is really, has support on a completely different set. So it's really. So if you're thinking about provers that's doing, on top of it, if I tell somebody, if you think of this as one writing down the proof, the fact that I'm going to look for this sort of means, whenever I'm going to look at this, I know the value of x. So the protocol really changes now. And so when you have to analyze this, you can't really sort of analyze, this should be prime also, you can't really think of this as analyzing, doing this by the Fourier transform, because this has a completely different flavor. Whoever is this unscrupulous prover, once he sort of see we completed the F table, then he actually, when he has to do this for C prime, he really already knows the value for x, so he can sort of think, well, what did I write here for this value of x? And in fact, he has partial information about the y, because whenever this is true, we can read off the value of y, and when this was false, it doesn't know any information, so it has partial information of y, so you can sort of get partial information of this. And you get into lots of interesting questions to try to understand Boolean functions when you sort of have probabilistic information on the inputs. So these intermediate questions, Z raises lots and lots of interesting questions. You know, if you have probabilistic information of Y, and you have some deterministic question of X, and you know you're going to compare one of these two, and you sort of have a betting game, which value should you take, and so forth. And I tried this a lot, and I couldn't make this fly. Okay. But you get into lots of interesting questions about Boolean functions. So that's why one way I would put it. I felt I tried a lot and killed, but you know, it's not that I wrote down that this doesn't work. But it sort of says that it could be these intermediate distributions that somehow can be used.
So that's for sure that you get to some constant. I mean, some optimal constant, which is not going to match with the constant you get from the unique game, right? Or is it clear that, like for instance, max cut, you will never be able to, even if you...
Well,
so that would prove the
somehow starting with this label cover and only doing bits like this, we're never going to get the Germanson-Williams constant for Tulin 2. That I think is true, yeah. But I couldn't make this fly.
Is there any reason why you cannot get the constant?
Let me... I have two more... How am I doing? So let me... I have two more things I want to say, and then we can talk, okay? So something I didn't use throughout this gadget reduction, I don't think TSSW were aware of, is that, in fact, if you look at the proofs, we actually have more than I was using just beforehand. We know in the good case of 3-lin, we always have a satisfying assignment, but on top of it, all the 4 satisfying assignments will appear equally often in this assignment. Okay. And also in the bad case, all 8, this will appear equally often. It's not like we just satisfy parity half the time, but all the 8 assignments are equally frequent. Okay? This is what I call uselessness.
So this is uselessness of what? What is useless?
Parity is useless. So predicate is useless if you can't distinguish the cases when you can almost always satisfy from the case when you get the almost uniform distribution on 3-bit strings.
What makes it useless? Why this fact makes it useless?
Well, in the paper where we prove this, I say that P is useful for Q. If I promise you can almost always satisfy Q, then you can do something non-trivial for Q. Okay, and the predicate is useless if you can't do anything useful for any Q, and that property turns out to be equivalent with this uniform. So that's why it's... So, since case... So using that fact, this is a gadget for 3-sat. for 2-sat from 3-lin. Okay. So if you have x times y times z is equal to 1, Sorry. So here you can satisfy all this. Yeah, well, you can satisfy 2 clauses, but you can do 3 if both x and y are true, because then you can set A1 to true. Or z is true, because then you can set A1 to true. Or, well, if these are both true, you can set A1 to false, and if this is true, you can set A1 and you satisfy all 3. And then you just check. Well, if the parity of this is 1, these things will never happen at the same time, because true is -1, so it can't be that all 3 are -1. So these 2 cases intersect nicely, while for a random string they're sort of independent. And if you work it out, you actually get 21 over 22 also with this simpler gadget. So you can, you're happy with this? Before I had very strong conditions, right? That if you had for each satisfying assignment, for when you satisfy the predicate, you would do well, and while for each non-satisfying, you would do less well. And in fact, I claim that all what I need is the property that if you, in the case of a random good assignment, you should have something good, and if a random assignment overall, you should do worse. And then that actually does for much simpler gadgets.
So that's because the instance you obtain with your type of checking of the long code.
Yeah, that's because you look deeper into the proof, and I didn't only prove the inapproximability results, I proved the stronger property. Okay. But it doesn't help, you don't get better results for neither 2SAT or 2LIN by this. You get smaller gadgets, but you get gadgets of the same quality.
And is it clear a priori that this is what's going to happen?
No.
It's just
that's the way it is. Okay.
But can you formalize the idea? So here it's in some sense just helping us to get rid of the symmetric parts, right?
Yeah, so the problem that's happening sort of is that the big gadgets take care of all the symmetries, and now the symmetries move over to the assignment parts, and somehow you get smaller gadgets, but not too much happens. So now the question: so you want to start with something better?
So sorry, just an add-on. So could you sort of try to actually say that they formally don't do better? So you take an assignment that assumes the symmetry, but you symmetrize and you look at it.
Yeah, so when you're looking at these symmetric things, this is just an LP also, as far as I remember. And the symmetric thing is still an LP. I mean, when you're taking these sums instead, it's a symmetric LP. I mean, still an LP, so you can check that the gadgets you get are optimal. That you can't do better. Okay. So, but really, let's have another starting point. So then the question is, what other starting point should we have? We should have some good inapproximability result. 3LIN was the champion so far. Can we possibly hope for a better starting point? Yes?
Can you try something non-binary? Do everything modulo 7 or something?
Yes, I didn't really try, but there's no reason that we couldn't start with a non-binary predicate and build something gadget on top of it. That's completely possible, yes. So if you do go from maxlink 2 to maxlink q for any, well, in fact m, if that matters, it doesn't have to be prime, inapproximability results does improve. It's basically the same proof. Okay. But this is actually a good starting point. So let's see to find an optimal gadget from this to SAT. Okay. So let's look more closely at, let's find an optimal gadget from this thing. Let's look a little bit more closely to the linear program I created. How many auxiliary variables did we have? But
You have exponential and cube.
yeah. If they had the number of satisfying assignments, I sort of got 2 to the number of satisfying assignments. Okay. And right?
What do you do with the original variables? They are no longer Boolean.
Yeah.
So you could,
The question is what to do with them.
You could use a code, but then you'll have to.
Yeah, okay. Yeah, maybe this maybe it was a bad time. Let's follow a different tangent,
No,
okay?
why was unnecessary? We just subtracted them so we didn't need to subtract. If you have enough auxiliary variables, then that's
no,
enough.
but you'll need constraints that
Just
use
encode them
the
in the
original.
usual binary form. Why do you need a code?
Yeah, why do you need?
Well, because it depends on what you're trying to reduce to. If you're trying to reduce to
No, encode them in the
Yeah, so
binary.
Guy's point is that, right, we sort of, the original variables are now mod Q, right, and I want to stick them into a tooling 2, and it's sort of, how do we code them, and the gadget is not really defined when we have different domains. So yeah, so it's clear that something, but I sort of picked this up on the fly, so which was a bad idea. So I had a different predicate in mind, in fact, to start with. So it's clear we should look for sparse predicates, right? The sparser predicate, it seems that the more powerful they are. We want sparse predicates with very good inapproximability factors.
So sparse, you mean the number of satisfying assignments.
Yeah, the number of things that it's had. And then if you were at this workshop 2 weeks ago, we actually have a very nice new predicate to work with. Okay. Yeah. So what he did, one of the things he does is that he has a 7-ary Boolean predicate with 8 satisfying assignment, which is in fact useless, with my definition of useless. So let's see what this predicate looks like. So this is in fact just a linear code of dimension 3, if you put it that way. Another way to say it, that's sort of the Hadamard code. So really it's just a linear space of dimension 3, and sort of the only one with not repeated coordinates. If you wanted sort of the Hadamard encoding, it's sort of the value of all non-trivial linear functions on each of the 8 inputs. This is 3 definitions basically saying the same thing. Can you see this? So if you label the coordinates by the linear functions, and the code words are for it. Right, this is corresponding to 1, 1, 1, this corresponds to 1, minus 1, 1. Right? These are the code word corresponding to inputs, these are the linear functions, and this is sort of the valuations. So this coordinate is always the XOR of these two coordinates. That's a new fresh bits, but then this is the XOR of this and this. This is the XOR of this and this and this, and this is the XOR of these three coordinates. That's the linear functions. So you get 8 inputs on 7 bits each, and this is a linear space and so forth.
Wait, so the satisfying assignments are the linear functions?
Yeah. Well, the
non-trivial.
I mean, the coordinates are. I mean, sort of all dual, right? But I think of the coordinates as given by the non-trivial linear functions. Sometimes it makes sense to have a constant bit also. And the correct evaluations, you know, is this an evaluation of all the linear functions on some input? But you could take the dual view, right? I view this as, you know, it's the Hadamard code where I take away the all zero. The Hadamard code of something is the value of all linear functions on this input, right?
Basically, it's a three-dimensional linear subspace minus the zero.
Yeah. If you want, we can add, sometimes when reasoning about these things, we can add a coordinate here that's all one in all the vectors, but that's sort of, and then it's really the full Hadamard code of each of the inputs. So this turns out to be, useless. It's hard to tell if you can satisfy all constraints of this form from when you can do a random 7-bit string.
No, it's unfortunate notation, right? Because you're hoping it will be useful.
Yeah. So we hope, is this useful for gadgets? Okay. So now when we're trying to investigate it, I sort of just hand-waved my way through these good constructions that we have only finitely many auxiliary variables, you know, we have only so many constraints, we have an LP, we solve it. So let's look a little bit more carefully what the LP actually looks like. Right? So if you look at the number of auxiliary variables, then in fact it was 2 to the number of satisfying assignments minus 1, minus the number of primary variables that we had minus 1. This is the constant we also. Okay. Which in our case is 121 minus 8, which is 120. Okay. So if we're thinking about going to 2-lin, then we have roughly 120 choose 2 times 2, which is, you know, 144,000 weights. Which is still manageable, but we have like 2 to the 120 constraints. Because we wanted something to be true for all auxiliary variables. Right, for all assignments to auxiliary variables. So this LP turns out to be difficult to run. Okay? So the point is now, I don't know if you can make a better gadget from this predicate to 2-lin or not.
It's not obvious. It's not of course, you don't want to write to you can't.
Yeah.
But you know that you can sometimes solve huge linear program just that it's enough you are able to.
Yeah, you can sort of have some separation oracle or go to the dual. Well, dual is not maybe not so good.
But if you can be your own separation and membership program.
Yeah, yeah. So it's not as, but you can't just take your LP off the shelf solver and do this. But
it's not a priori clear that this is
no. This has been I was trying to convince my graduate students to do this for a while, but they would not. Okay. So I'll tell you a little bit. So I'll play with this for a while. So always when you can't solve a problem, you can always look at a different problem. So if you instead, I've sort of done max tool in 2 so far, right? I mean, try to satisfy as many equations as possible, and then you could get 11 over 12. But let's do min 2, try to minimize the number of false equations instead. Okay. And and since, of course, it's very related to max tool in 2, I can just look at the reduction I just had for the reducibility of max tool in 2, and that actually gives 5 over 4. And this was sort of the best constant known for a long time. Okay? So if we call this H7, this predicate, you know, this is H 2 to the k minus 1 in general for general k. So H7 is the 7-dimensional thing, and of course you can generalize it. And their chance result applies to all these things. Then in fact you can get 11 over 8 here by gadget from this Chant predicate. So you know, this turns out to be incredibly symmetric, and I wrote down a gadget that actually gives you 11 over 8 and checked it by computer. Yes?
Is there any approximation algorithm for this problem?
If you assume unique games, it's hard to approximate within a constant. So but now when you're sort of thinking, going to what Mario said, is it completely impossible that you should get the Gamma-Williamson constant on these things? Well, it could be quite possible that you have an infinite family here of very hard constraint satisfaction problem and a family of gadgets that actually tends to a very strange number.
No, but everything seems to be rational here. I mean, how are you going to get the Goemans waves to come through?
You could just get a sequence that tends to the Goemans.
But so you might get the Goemans-Williamson perhaps, but you cannot get the unique game. I mean, the unique game is just yet another approximation problem. And if you could get the unique game, then you would have proven the NP hardness of unique game, right?
Yeah, so what's wrong with that?
Sorry?
What's wrong with that?
There is nothing wrong with that, but yeah, I don't know what's wrong with that.
So the challenge now is to understand, now we're back to the 70s here, that we actually have to understand these gadgets by hand, or by, being a very clever programmer. Okay? So I would be interested to see if anybody's, willing to program here to try to figure out the optimal reduction from this gadget, from this thing to either 2-lin or 2-sat or max cut. It's not completely out of the question, even though it's non-trivial.
actually, there could be something wrong with. I'm sorry, I'm just answering that there could be something wrong with that, because there is this new, I mean, not so new result that you can do the unique game actually faster than 2 to the n.
Yep.
Right? And if you could do it with gadget reduction, then this would contradict to the exponential time hypothesis.
No, well, but then that's a very good point, which I haven't really keep track of, right? That I'm just talking now polynomial size, and I have arbitrary constants, and the question is, if you would assume that suppose you want to assume the exponential time hypothesis, right? Then if you sort of look, then it's very difficult. I've always gotten this, I've used the parallel repetition, and the size of the parallel repetition has been n to the k, where this k is sort of related to the soundness I want. So all the results I've described has very, a 2 to the square doesn't rule out the 2 to the square root n algorithm for approximating, say, max 3 lin. But then you have to use other results, either starting PCPs or not apply the parallel repetition, where you don't get a blow up. You can sort of get label cover where you don't get the blow up that depends on epsilon, like Moscowitz routes. So then you have to start keeping track of how does the polynomial blow up do, and you don't want this big blow up as I'm paying with the parallel repetition. So here is nothing really excludes. I mean, I have huge polynomial blow ups all over the place. I'm not doing so well here. I'm not really sure what to do next. One thing I was going to do is maybe try to prove this result by chunk. That these are approximation resistant, or we could, but 5 minutes I don't think it actually makes sense to really set it up, but then I'll start doing that tomorrow in such a case, if there are any more questions.
So doesn't the LP have a lot of symmetry?
Yes.
Because you're essentially picking rows of the whole truth table on 2 to the n. Like you pick these 8 rows, and you have all combinations of vectors for these.
Yeah. Yes, it's. You can think, so you can think, maybe you don't need. So this gadget, for instance, uses all auxiliary variables.
All variables.
Yeah, and it does use it also the uselessness. It doesn't. It's not a strict gadget in the sense it uses the uselessness. Okay. But you could sort of, once you're using the uselessness, maybe you don't. I mean, maybe you could make a less symmetric gadget than this. It doesn't use everything if you're going to, and use a little bit more of the uselessness. But sure, there are lots of symmetries here, right? So you could hope to get by with much fewer variables. But if you're going to write down an honest and use some LP prover, you really have to make this down very much, and then otherwise you need some of these implicit things. So another thing to if you just want to beat the 11 over 12, we can note that this predicate implies lots of parities, right? The XOR of the first 3 bits is 1. There are lots of other XORs. So you have lots of parity gadgets sitting in there. You can just take a parity gadget, and that will actually give you equally well. So it's clear that you're going to get 11 over 12 from max 2 lin here. And you can even make a very symmetric point, and you can ask, is this a local optimum for this linear program, or can we do some steepest descent from there? And I was not able to. Well, I didn't try myself there, but I wasn't able to convince somebody else to.
This is a boot camp. You can tell us.
Well, since I told you easy homeworks, that's 5 minutes of work. This is at least, many hours of work. But maybe that's. And I'll stop here and then continue tomorrow.